Hello everyone and welcome back. Today we're going to be going through a couple applications of linear systems. So the first one is usually referred to as a mixture problem. So let's see if we can work through it together. Suppose we have 800 gallons, or we desire 800 gallons of 89 octane gasoline, and we seek to obtain this 89 octane gasoline solution by mixing 87 octane with 92 octane, right? So in some sense, we're sort of averaging the concentration of the 87 and the 92 octane gasoline solutions to build something in the middle, in particular an 89 octane gasoline solution. So if we want 800 gallons of this 89 octane solution, how much of each of the 87 and 92 solutions must be mixed together to get our 800 gallons of 89? All right, so the first thing that we need to do is identify the variables that we're going to be working with. So we're going to let X represent the gallons of 87 solution, and we're going to be letting Y be the number of gallons of our 92 solution. Once you have these defined, now we can start building our solutions. So keep in mind we're going to be mixing some amount of 87 together with some amount of 92 solution, and we want that total gallon to be equal to 800. So the focus of this equation is going to be the volume. And the next equation that I want to focus on is going to be the concentration equation. So we have 87 of the 87 concentration of the 87 octane solution, and then totaling with 92 with the gallons of the 92 octane solution. And that together must be equal to what type of concentration? In particular, we want that to be an 89 solution. And of course, we're going to have x plus y of that. Okay, so notice concentration, volume, concentration, volume, concentration, and volume. Okay, so this is pretty much referring to concentration, density, whatever you want to call it, but I'm going to call it concentration. Right? So what we have here is we have a system of two linear equations, two unknowns, x and y, and our goal is to solve that system. So the first thing I want to do is I'm going to distribute this 89 on the right hand side and then shift both of those over to the left hand side. So we're going to have 87x minus 89x and 92y minus 89y. So once I rearrange that, that's going to give us the system x plus y is equal to 800 and minus 2x plus 3y is equal to 0. We can easily represent this as a matrix equation if you're more comfortable with that, or you can use Gaussian elimination on this system of equations. Whichever way is more convenient for you is perfectly fine with me. So I'm going to approach this from the matrix perspective. So our coefficients is going to be equal to 1, 1, minus 2, 3 with unknown variables x and y, and that's going to be equal to 800 and 0. I'm going to be calling this coefficient matrix, I'm going to be calling that A just for now. And we see that the determinant of that matrix A is going to be equal to 1 times 3 minus 2 times 1. So it's going to be 3 plus 2, which is going to come out to 5. So if that's true, that means we can easily find the inverse of that matrix. So the inverse of that matrix is going to be equal to 1 divided by the determinant of that matrix. Then we're going to reverse the primary diagonal entries. So instead of 1, 3, we're going to have 3, 1, and then we're going to negate the off diagonal entries, and we're going to have that. So that's the inverse of our matrix A. So if I want to solve this equation for xy, I'm going to multiply both sides on the left by the inverse of matrix A, and I'm going to have that xy is going to be equal to the inverse of that matrix A, which is going to be 1, 5 times 3 minus 1, 2, 1 times this vector 800 and 0. So once I multiply that matrix and that column vector together, that's going to come out to the matrix 2400 and 1600, and don't forget to divide by that by 5, and we're going to have 480 and 320. So that means in order to obtain our 800 gallons of 89 octane solution, we need to mix together 480 gallons of 87 octane, and we need to mix that with 320 gallons of 92 octane solution. And you should be able to verify that the solution does check out with both of the equations that we set up before. In particular, if we add these two together, we will get a total volume of 800 gallons. Now let us consider this next example. Due to gravity, a projectile will follow a parabolic path. If an object is fired from a height of 10 feet above the ground, has a height of 14 feet after 1 second and 3 feet after 5 seconds, give a model of height as a function of time. So every time you have something that relates to like physics or geometry, sometimes drawing a picture will be a little bit helpful. So what I'm going to do is I'm going to draw, for example, the ground to be equal to the horizontal x-axis, and I'm going to let the vertical axis represent the height as a function of, for example, time. So if anything, that's going to be the time axis. So what we have here is if it sits on the horizontal axis, that's going to have a height of 0. So that means it hits the floor. So after 0 seconds has passed, we have an initial height of 10 feet. So this is going to be my 10 feet. And we're assuming that this is going to be a parabolic path, in particular a negative parabolic path, because whatever comes up must come down, at least by the traditional laws of physics. So our parabolic path is going to be equal to this particular curve, right? And once it hits the ground, let's assume that it doesn't keep on going through the ground. So if we have this equation, h of t, written out, which we're assuming to be a parabolic path, that means this equation can be written in the form at squared plus bt plus c, where a, b, and c are constants that we eventually are going to find. Once we have this constant, for example, we can find the maximum height of the projectile, we can find out how long it takes for it to hit the ground, and several other things, which we won't get into now. Alright, so what do we know? So after 0 seconds has passed, we know the height is going to be equal to 10. So if you plug in 0 everywhere we see t, notice that at squared and bt will go away, leaving us with c is equal to 10. So that gives us one coefficient of our quadratic model. Now we need to use the other pieces of information. In particular, it has a height of 10 feet above the ground at initial state, so we've already used that. We have a height of 14 feet after 1 second and 3 feet after 5 seconds. So we need to use those pieces of information. So how are we going to do that? So after 1 second, it has a height of 14. So h of 1 is going to be equal to a times 1 squared plus b times 1 plus c, which we know to be equal to 10. And that height should come out to 14. And after 5 seconds, so h of 5, which is going to be equal to a5 squared plus b times 5 plus 10, that's going to be equal to 3. Right? So those are two equations with two unknowns, in particular a and b, so we need to find them. So we should be able to use linear algebra in order to generate those solutions. So what I want to do is just clean this up a bit. So we have a times 1 squared, that's just a. We have b times 1, that's just b. And then we have 10 is equal to 14. We can subtract that 10 from both sides, and then we're just going to have 4 on the right-hand side. So we're going to have a plus b is going to be equal to 4. And then over here we have 25a and 5b. So 25a and 5b is equal to 10 is equal to 3. So we can subtract 10 from both sides to get minus 7. All right, so we can write this as a system of equations or perform Gauss-Jordan elimination directly, whichever one you prefer. So we're going to have 1, 1, 25, 5 times AB is equal to 4 minus 7. I'm going to call that matrix, I'm going to call it A as usual. So the determinant of A is going to be equal to what? So we're going to have 1 times 5 minus 25 times 1. So that's going to be 5 minus 25. That's going to be equal to minus 20. So that means the inverse of that matrix is going to be equal to 1 divided by negative 120. Reverse the primary diagonal elements, so we're going to have 5 and 1, and then we're going to have minus 1 and minus 25 to be the inverse of that coefficient matrix. So to solve this equation, we're going to multiply both sides on the left by the inverse of A, and we're going to have AB is equal to the inverse of A, so negative 1 over 20, times 5 minus 1 minus 25, 1, times that vector 4 minus 7. Once we multiply that out, so 5 times 4 plus negative 1 times negative 7, that's going to come out to 27. And then minus 25 times 4 plus 1 times minus 7, that's going to come out to negative 107. So this is going to come out to negative 1 over 20 times 27 and negative 107. And once you distribute that negative 1 over 20m, that's going to come out to negative 1.35 and 5.35. Keep in mind this leading coefficient is corresponding to a, which should be negative because it should be an upside down or concave down parabola, i.e. its vertex must be a maximum. Right, so we have our A, we have our B, and we know that C was equal to 10. That means our model for our height at any time t is given to be negative 1.35 t squared plus 5.35 t plus 10. And using this equation, you should be able to verify that all three of those points do satisfy. And you can also use this equation to model the height at any time t for which you are interested in. Now let us consider this example. Suppose we have an airplane that travels between cities A and B, and let's also assume that it travels between B and A also, such that the distance from A to B is 2,400 miles. Let's also assume that from A to B, there's a constant, never-ending headwind. So of course, before going through the problem, sometimes it's just important to interpret this in bite-sized chunks. So what we have here is we have, for example, city A located here and city B located here, and let's assume that's the path from A to B. So if we have a constant headwind when we travel from A to B, that means once we travel in that direction, that means we're going to have wind that is going to be opposing us. So our wind is going to be located in that particular direction. So that's going to be slowing us down, right? So that's our wind direction. All right. And also when we travel in the other direction, so when we travel from B to A, the wind is actually going to be in our favor and actually isn't going to sort of hinder our speed, right? So generally speaking, the average speed from A to B should be less than the average speed from B to A by some margin. All right, so with that being said, if the plane has a constant speed and the air also has a constant speed and also direction, right? So the wind is going to be going from B to A, but it's not going to shift directions once we shift directions or anything like that. So what are the speeds of the plane and also the wind, provided that it took the plane 4 hours to go from A to B and 3 hours from B to A? Right, and these times make, of course, sense, right? So if the wind is going in the direction from B to A, then it should take a little bit longer to travel from A to B versus from B to A, right? So if there wasn't any wind, then it should take somewhere between, say, 3 and 4 hours. So what I want to start off by doing is just labeling the speeds that we seek to find. So we're going to be letting x represent the airplane speed. So x is going to be the airplane speed, and y is going to be the wind speed, right? And we want to find both of them. There's going to be one equation that we need to know here because we have some speeds, we have some times, and we have some rates, right? So you should know that distance can be represented as rate times time, or you may have seen this written in the form rate is equal to distance divided by time. They're the same exact equation, just solved for different variables, right? Now we're going to have two different rates here, right? We have the rate from A to B, and we also have the rate from B to A. So let's look at this from this perspective. So the rate from A to B, so we're going to be focusing on that particular perspective, is going to be equal to the distance from A to B, all divided by the time it takes to get from A to B. And we also know that the rate from B to A is going to be equal to the distance from B to A divided by the time it takes to get from B to A. Right, now we have two different rates actually here. We have the rate for the airplane, and we also have the rate for the wind. So it's sometimes safe to approach these rates as the net rates. So these are going to be the net rates. So, you know, it has both the airplane and the wind into it, and if we sort of decompose these net rates into airplane and wind rates, then everything will be perfectly fine. Now, one thing can be simplified immensely here, in particular dA and dB. We know that dAb and dBA are going to be the same, and let's assume that both of those are going to be 2,400 miles. Because sometimes these distances are not the same, because sometimes we don't have the ability to travel in the same direction. Sometimes we have to go around something, especially if there's like one-way streets or something like that, or one-way flight paths since we're in an airplane. All right. Now, we need to build some equations here, right? So let's think about this equation just one last time, right? So let's assume we have this A and this B here, right? We have to develop these equations. So what can we get from this distance is equal to rate times time thing, right? So from the net speeds and those net speed equations, we have that the rate from A to B is going to be equal to the distance from A to B, so 2,400 divided by 4, right? So that's going to be equal to 600 miles per hour, right? So that is the net speed for the airplane and the wind. And also the rate from B to A, that's going to come out to 2,400 divided by 3, which is going to be equal to 800 miles per hour. Now let's think about this rate from A to B equation in just a little bit more depth, right? So keep in mind that our wind is traveling in that direction, and we know that the average or the net rate from A to B is going to be equal to 600. So the speed of the airplane needs to overtake that in order to get from A to B. So if that is the case, at least from basic physics principles, that means that x must be greater than 600. That means the speed of the airplane has to exceed 600 in order for us to overtake that particular speed, right? So if x is bigger than 600, that means there must be some other speed y such that x minus y must be equal to 600. And that speed is, of course, going to be that wind speed, right? And of course, once we go in the other direction, the wind and the airplane are working together. So we're going to have that x plus y must be equal to that 800 in the other direction. Right, so that's going to give us our two linear equations to work with. So we can, of course, jump to a matrix equation. 1 minus 1, 1, 1 times x times y. And that's going to be 600 times 800. Let's call this matrix A just to get a working knowledge of what's going on here. So the determinant of A is going to be 1 times 1 minus minus 1 times 1. So that's going to be 1 plus 1, which is going to be equal to 2. So that means the inverse matrix is going to be equal to 1/2, and then we're going to reverse those. Not much to reverse though, and then we're going to negate those elements. Then we can solve this equation for x and y. So we're going to have that xy is going to be equal to the inverse of a, so 1/2 times 1, 1 minus 1, 1 times 600 times 800. And keep in mind, for x we should be getting a number that is bigger than 100, or bigger than 600 rather. And then for the other direction we should have a number that is going to be less than 600. Or the difference should sum out to 600, right? So once we actually work that out, that's going to come out to 1/2 of 1400 and 200, which is going to come out to 700 and 100. And those are the speed, or the average speed, of the airplane and the wind, right? So that means the speed of the airplane is going to be 700 miles per hour, and the speed of the air in that direction from B to air is going to be 100 miles per hour, right? And those are three basic applications that we can use linear systems for, and we'll be looking at a few other applications a little bit down the line. So I hope you enjoyed, and I'll see you in the next video. Take care.